My organization is nice. Here's how I keep track of all my things. I start by writing down everything that needs to get done. Next, I set a priority and a due date to keep paying track. I create custom statuses to organize my progress and exact deadlines.
Eu vou, essas slides então aí eu vou pegar, acho que ela mandou pro meu e-mail, só um minutinho, tá? Acho que tá tudo aparecendo lá na transmissão. É melhor eu não fazer por lá. Eu vou passar por aqui, mas o que eu preciso te mostrar aqui é o seguinte. Acho que eu deixei no canal. Eu achei que já estava aqui. Eu vou colocar lá no fundo, mas é assim. Esse cara aqui que você vai precisar é assim. Você não entende de pressionado, tá vendo uma ondinha aqui? Ó, ele mexe no espaço. Só que eventualmente ele desalinha. Sempre que desalinhar, você solta, seleciona de novo e vai, tá bom? Você toma cuidado que o seu slide está em PowerPoint, as duas versões. É só que é assim, ó. É dependendo de conforto, se você dá um clique apenas, isso vale um clique de mouse. Tá? Então vai pra frente. Então, se você clicar pra frente por engano, você volta para esse último. Aí tem pointer? Esse aqui é pra frente. Não, o pointer é isso aqui que vai pra frente. Tá. Entendeu? Então, pera. Então, você se eu aperto e segura o pointer. É o pointer. Tá aqui. Tá bom. Pra ir pra frente é um clique rápido, é isso? Isso. Mas o ideal é usar esse grandão aí. E a outra coisa que eu estou procurando agora é ver onde que o palestrante que estava aqui antes deixou o microfone, meu. Não posso falar, vamos discutir. Eu não acredito. Eu acho que ele pode usar esse aqui, mas eu vou ver se de repente na correria ele me entregou e eu coloquei lá. Vamos começar então com esse, né? E eu vou ver se eu acho o Alô?
O mais importante é colocar o seminário dele aqui, né? Para não poder crescer.
Sim, eu já vou colocar.
Obrigada.
Cima eu coloco, tá?
Boa tarde. Nos desculpem todo o atraso. O palestrante de hoje é Roberto Bertoldo Menezes, do Instituto Mauá de Tecnologia. O Roberto é da casa, fez o bacharelado aqui na FISCA, em Ciências, fez o doutorado, fez o mestrado e doutorado aqui em IAG, fez um pós-doc também aqui em IAG, tudo com o João Steiner, depois fez um pós-doc na UCBC, e depois finalmente está lá na Mauá desde então. Né? Ele vai falar sobre the use of machine learning for the classification of the nuclear emission of galaxies. Seja muito bem-vindo, muito obrigada, Roberto. Microfone em inglês. Ah, desculpa, eu fiz a sua apresentação em português, mas a sua fala em inglês.
Hello? Good afternoon, everybody. I'm going to talk about the use of machine learning for the classification of the nuclear emission of galaxies and of stellar light curves. So the main goals of this project were these two. So first, to develop a methodology with machine learning to classify the nuclear emission of galaxies in Seyferts, liners, and H2 regions using only photometric parameters. Because this kind of classification is usually performed with spectroscopic parameters. So in this case, in order to have something new, we try to perform the classification using only photometric parameters. And second, to develop a methodology, again, with machine learning, to classify stellar light curves in curves with eclipses caused by exoplanets, curves with eclipses caused by eclipsing binaries, and curves without eclipses. Okay? And these two goals are actually related to very different areas in astrophysics, but these two topics have something in common. They are both very suitable for analysis involving machine learning. So machine learning is what actually connects them in this case. So for this entire project involved the work of these undergraduate students here, all from Instituto Mauá de Tecnologia. So Tiago and Arthur worked in the classification of the nuclear emission of galaxies, and Guilherme, Leonardo, and Pedro worked in the classification of stellar light curves. And for the first part of my presentation, I'm going to talk about the use of machine learning for the classification of nuclear emission of galaxies. And I'm going to start with a brief introduction. So certainly, one of the most relevant sub-areas of extragalactic astrophysics involves the analysis of the nuclear emission of galaxies, as such a study can provide important information about the process of formation and evolution of galaxies. And it is well known that the nuclear emission from some galaxies cannot be attributed only to the stars there. These are the so-called active galactic nuclei, or AGNs for short. And today it is well established that the energy emitted by AGNs comes from the accretion of matter onto central supermassive black holes in these objects. In this case, the material spirals and falls towards the central supermassive black hole, originating this structure called accretion disk. And in this process, part of the gravitational potential energy of the material is converted into thermal and radiative energy, which is emitted, originating all the observed energetic phenomena in AGNs. And according to their observed properties, AGNs can be classified in different categories, such as the quasi-stellar radio sources, or quasars for short, which are the brightest objects of this class, radio galaxies, Seyferts galaxies, and also the low ionization nuclear emission-line regions, or liners for short, which have a lower ionization degree than other AGNs. And we have also, of course, galaxies whose nuclear emission comes mainly from gas photoionized by hot young stars, which is characteristic of H2 regions. And usually, the classification of the nuclear emission of galaxies is performed with spectroscopic parameters using the so-called diagnostic diagrams. And for those of you who may not be familiar with this, diagnostic diagrams are essentially graphs relating two emission line ratios. These three are the most used diagnostic diagrams to perform this kind of analysis. These are the so-called BPT, or Baldwin-Phillips-Terlevich diagrams. All of them show the oxygen 3 over H beta emission line ratio on the vertical axis. This line ratio essentially measures the ionization degree of the objects. And since Seyferts have a higher ionization degree than liners, this line ratio here essentially distinguishes between liners and Seyferts. On the horizontal axis, we can have the nitrogen 2 over H alpha, the sulfur 2 over H alpha, or the oxygen 1 over H alpha emission line ratios. These line ratios essentially indicate the relevance of possible partial ionization regions in the observed objects. Now, partial ionization regions are much more relevant in AGNs than in H2 regions. So these emission line ratios here essentially distinguish between AGNs and H2 regions. So in summary, by combining all these emission line ratios here, we can classify the nuclear emission of galaxies in H2 regions, the blue points here, Seyferts, the green points here, and liners, the red points here. And this is certainly the most used method to classify the nuclear emission of galaxies, but it has its own disadvantages. One of these disadvantages is that it requires spectroscopic parameters, which are, let's say, harder to be obtained than photometric parameters. And another disadvantage is that this method can result sometimes in imprecise classifications, because one galaxy, for example, may have one classification in one diagram and another classification in the other diagram. That can happen. So considering that, methodology to classify the nuclear emission of galaxies using photometric parameters is certainly desirable. And this kind of analysis usually involves large amounts of data. And considering that, machine learning algorithms are certainly an interesting idea to be used in this case. And machine learning algorithms, for those of you who may not know about it, are usually divided in supervised and unsupervised. Supervised machine learning algorithms are used to learn relations between sets of variables based on known examples. And once this training or learning is complete, the algorithms can be used to predict the behavior of other datasets. Unsupervised machine learning algorithms, on the other hand, do not use examples to learn relations between sets of variables. Instead, these algorithms include a great variety of statistical tools to perform different types of data analysis, such as clustering, which corresponds to dividing the data in different groups based on the observed properties, dimensionality reduction, detection of outliers, among others. Supervised machine learning algorithms are the most used in astronomy. And in this project, we tested 4 different machine learning algorithms. The first and the simplest one was this, decision trees, which is a supervised algorithm. Decision trees are essentially these structures here, similar to trees, in which a simple decision is taken in each of these nodes here. And with all these decisions, the algorithm can divide or classify an initial data sample in different groups, for example. The procedure works like this. First, you provide to the algorithm an initial data sample with all the classifications in these groups here already known. And based on this initial sample with the classifications already known, the algorithm constructs an adequate decision tree to recover all these classifications correctly. And once this training is complete, the obtained decision tree can be used to classify other data samples in these same groups. That's how it works. The second machine learning algorithm we tested in this work was this, random forests. Random forests are essentially collections of decision trees. And during the training of this method, each of these decision trees receives a random subset of the original data set. And after the training is finished, and once the algorithm is applied to other data sets, the final results are always obtained, taking into account the results provided by all these decision trees together. The third and most advanced machine learning algorithm we tested in this work was this, extreme gradient boosting, or XGBoost for short. So this method is also based on decision trees, but instead of building decision trees independently, like random forest, for example, XGBoost actually builds decision trees sequentially, one after the other, with each new decision tree correcting the errors from previous ones. After each new decision tree is built here, the algorithm applies a gradient descent method to minimize the so-called loss function. The loss function essentially quantifies the differences between the algorithm's predictions and the true values. So during the training of this method, the algorithm always seeks to minimize this loss function so that the algorithm's predictions become more and more accurate. That's how it works. And the final machine learning algorithm we tested in this work was this, Gaussian mixture models. This is an unsupervised machine learning algorithm. It is actually a probabilistic clustering technique, which means that it divides the data in different groups based on the observed properties. This method assumes that the data sample corresponds to a combination of several Gaussian distributions, and then the algorithm divides the data in each of these Gaussian distributions. But instead of rigidly assigning each data point to each Gaussian distribution, this algorithm actually calculates the probability of each data point to belong to each Gaussian distribution. And this flexibility actually allows this method to capture more, let's say, complex structures in the data in comparison to simpler methods. Now, for the classification of the nuclear emission of the galaxies in this work, we used a data sample with nearly 40,000 galaxies, with spectroscopic data from Sloan, and with photometric data from S+, the Southern Photometric Local Universe Survey. The spectroscopic parameters we used in this work were simply the integrated fluxes of these emission lines, so H-alpha, H-beta, oxygen 3, nitrogen 2, and sulfur 2. We did not use the integrated fluxes of the oxygen 1 emission line because this line was simply not available for many galaxies in our sample, probably because it's very faint, especially in H2 regions. And the photometric parameters we used in this work were simply the magnitudes of the galaxies in these broadband filters here, R, G, I, Z, and U, and in these narrowband filters. These narrowband filters essentially include the most intense emission lines in the optical spectrum. Now, in order to train the machine learning algorithms and also to evaluate the accuracies of the methods, we needed a preliminary classification of the nuclear emission of the galaxies in our sample. In order to obtain that, we performed a simple diagnostic diagram analysis with these two diagrams here. So we have oxygen 3 over H-beta as a function of nitrogen 2 over H-alpha, and oxygen 3 over H-beta as a function of sulfur 2 over H-alpha. We did not use the diagram involving the oxygen 1 over H-alpha line ratio because, as I mentioned, oxygen 1 was not available for many galaxies in our sample. So these are the results of this preliminary classification of the nuclear emission of the galaxies in our sample. Then we took the galaxies that had the same classifications in both of these diagrams. These objects with the same classifications in both diagrams were considered as having clear classifications. Then, these objects with clear classifications were used to train the machine learning algorithms after that. So, in other words, in this work, we used the results of these diagnostic diagram analysis here as the truth to train the machine learning algorithms after that. Okay? And as a first test of the machine learning algorithms, we tried to perform the classification here using only spectroscopic parameters as input. The main goal of this project does not involve using spectroscopic parameters to classify the nuclear emission of galaxies. But we decided to perform this initial test with spectroscopic parameters only to check whether or not these 4 machine learning algorithms were adequate for this kind of classification here. So in this case, in this initial test, we used as input parameters these simple line ratios here. Oxygen 3 over H beta, nitrogen 2 over H alpha, and sulfur 2 over H alpha. And for the supervised machine learning algorithms, 70% of the sample was used for the training, and the remaining 30% was used to test the results. And these are the accuracies we obtained for all the machine learning algorithms. These accuracies essentially correspond to the ratios between the correct predictions made by the models and the total number of objects. And as we can see, the accuracies are very high, all above 90%, most above 95%. But that's not really a surprise here, because these emission-line ratios here are normally used to classify the nuclear emission of galaxies. So it was kind of expected that the accuracies here would be high. Anyway, this initial test at least shows that these 4 machine learning algorithms here seem to be adequate for this kind of classification. And now we proceeded to the main part of our data analysis. And we applied the 4 machine learning algorithms using as input parameters the photometric parameters from S+. So we used these 5 broadband magnitudes here and these 7 narrowband magnitudes here as input, plus 1 additional parameter, the redshifts of the galaxies. Our data sample actually only included nearby objects, so the total redshift range of the objects was not very high. Anyway, we preferred to include the redshift as an additional input parameter. And these are the accuracies we obtained using all these photometric parameters as input. And again, the accuracies are very high, most above 95%. In order to analyze these results in further detail, we can take a look at the confusion matrices. For those of you who may not be familiar with this, confusion matrices are a very important tool to evaluate the accuracies of machine learning algorithms. Because instead of providing only global accuracies, like these, confusion matrices provide accuracies for all classes of objects considered in the data analysis. So these are the confusion matrices obtained with random forest and XGBoost for this classification of the nuclear emission of galaxies using photometric parameters. And on the vertical axis here, we have the true classifications of the galaxies obtained from the BPT diagrams. And on the horizontal axis, we have the model's predictions. So if we take a look at these confusion matrix here from XGBoost, we can say that 95.9% of the H2 regions in our sample were correctly identified by the model. 95.6% of the Seyferts in our sample were correctly identified by the model, and 95.70% of the liners in our sample were correctly identified by the model. And in the case of random forest here, we have a very similar pattern. So basically, the accuracies are all very similar and very high for all classes of objects considered in the data analysis. So based on all these results, we can say that a reliable classification of the nuclear emission of galaxies with machine learning using only photometric parameters as input is possible. But one natural question at this point is, do we really need all these 13 photometric parameters to obtain a reliable classification? In order to answer that, we performed 2 additional tests. We applied again the machine learning algorithms using only the narrow band magnitudes plus the redshifts as input parameters, and using only the broadband magnitudes and plus the redshifts as input parameters. These are the accuracies we obtained using only the narrow band magnitudes as input parameters, and again, they are very high, all above 95%. But that's not so hard to explain because, well, these narrow band filters here, as I mentioned, basically include the most intense emission lines in the optical spectrum. And since these lines are normally used to classify the nuclear emission of galaxies, it's not really a surprise that this analysis, using only narrow band magnitudes as input, worked, in this case, to classify the nuclear emission of galaxies. Now, these are the accuracies obtained using only the broadband magnitudes plus the redshifts as input. And again, the accuracies are very high, all above 95%. And that's not so easy to explain because, well, since these are broadband magnitudes, they do not reflect the properties of single emission lines. One possible explanation for this success here is that these broadband magnitudes essentially reflect the properties of the spectral energy distributions, the SEDs of the galaxies. And since SEDs can be used to classify the nuclear emission of galaxies, that's a possible explanation for why this analysis using only broadband magnitudes worked to classify the nuclear emission of galaxies. These are the confusion matrices obtained, in this case with XGBoost, just as an example, using only narrow band magnitudes as input and using only broadband magnitudes as input. And the patterns here are actually very, very similar to what we had seen here in the other confusion matrices obtained for the analysis using all photometric parameters. So again, the accuracies are very similar and very high for all classes of objects considered in our data analysis. Okay, now for the second part of my presentation, let's talk about light curve classification. And again, I'm going to start with a brief introduction. So stellar light curves are essentially graphs of the brightness of stars as a function of time. And these graphs can be used to detect possible variabilities in the brightness of stars along time. And brightness variations in stellar light curves can be caused by internal or external processes. Internal processes may include pulsation, rotations, things like that. External processes mostly include eclipses, which occur when a body orbiting the star passes between the star and the observer, resulting in a reduction of the brightness of the star, which can be detected in the light curve. And in this project, we are actually interested in eclipses. If we have, for example, an exoplanet orbiting a star, and the exoplanet passes between the star and the observer, the result is an eclipse, which has this profile in a light curve. But we can also have a second star orbiting the first one. If this second star passes between the first star and the observer, the result is also an eclipse, which can be detected in a light curve. These objects are called eclipsing binaries. These are examples of real stellar light curves with an eclipse caused by an exoplanet, and an eclipse caused by an eclipsing binary. And a very important point here is that it is very difficult to distinguish between an eclipse caused by an exoplanet and an eclipse caused by an eclipsing binary just by looking at the light curve. Usually, the classification of stellar light curves in curves with eclipses caused by exoplanets and curves with eclipses caused by eclipsing binaries is performed using specific modelings. And in the case of exoplanets, for example, these modelings provide a number of parameters of the exoplanets, such as their radii and the distances between the exoplanets and the stars they are orbiting. However, space telescopes, such as COROT, Kepler, and TESS from NASA, provided light curves for thousands of stars. So a manual analysis of these light curves of such a large amount of data is essentially impossible. In this context, the use of machine learning techniques here is also an interesting idea. So for this work, we used a data sample with 930 light curves. 1/3 of this sample contained eclipses caused by confirmed exoplanets. 1/3 of the sample contained eclipses caused by confirmed eclipsing binaries, and the final third contained no eclipses whatsoever. All these data were retrieved from the Kepler Public Data Archive, and these classifications of the light curves we are using here were obtained from the literature. Now, our purpose here was to develop a pipeline with machine learning to automatically classify light curves in those three categories that I mentioned. So, curves with eclipses caused by exoplanets, curves with eclipses caused by eclipsing binaries, and curves without eclipses. And for this classification, we concluded that the best option was to use the periodograms of the light curves as input parameters. Now, for a signal like this, a periodogram is proportional to the squared modulus of the Fourier transform of the signal. So basically, the periodogram shows the weights of each frequency component here on the original signal. This is an example of a real stellar light curve with these eclipses here caused by an exoplanet, and this is the corresponding periodogram. So in this work, the classification of stellar light curves was performed using periodograms as input parameters. We also opted to include in our pipeline the use of the Butterworth filtering to remove high-frequency components from the light curves before the machine learning algorithms were actually applied. The presence of instrumental significant high-frequency noise in stellar light curves is very common, and such a noise can affect the data analysis. That's a fact. So in this work, we applied the Butterworth filtering to remove part of this high-frequency noise without affecting the general profiles of the light curves. So this is an example here of a real stellar light curve, the black line here, with an eclipse caused by an exoplanet. And superposed, the red line, we have the same light curve after the Butterworth filtering. So we can see, maybe it's difficult for you to see, but the filtering process removed part of the high-frequency noise. But the effect of the filtering here was not so dramatic. And that was necessary because a more, let's say, intense filtering of this light curve would probably also alter the general profiles of the light curve, and we did not want that. But although the noise removal here was only moderate, we noted that this noise reduction provided by the Butterworth filtering resulted in detectable improvements in the accuracies of the machine learning algorithms. So in the end, we concluded that the use of the Butterworth filtering in our pipeline was worth it. So these are the main steps of our pipeline for the automatic classification of stellar light curves taken with any instrument. So first, we apply a resampling of the light curves so that in the end, all light curves have the same time sampling and cover the same total time interval. Then we apply the Butterworth filtering to remove high-frequency noise from the curves. And then we obtain the periodograms of the light curves. After a detrending procedure, this detrending procedure corresponds to essentially subtracting a constant value from the light curves so that in the end there is no zero frequency component in the periodograms, which can affect the data analysis. And after that, we train the machine learning algorithms using classifications obtained from the literature. And once this training is done, we can apply the algorithms to classify light curves from other data samples. These are the accuracies we obtained for our 4 machine learning algorithms during the classification of stellar light curves. And we can see that the situation here is somewhat different than what we obtained for the classification of the nuclear emission of galaxies, because the accuracies obtained with simple decision trees and with Gaussian mixture models were actually quite low. On the other hand, the accuracies obtained with random forest and especially with XGBoost were very high. XGBoost was the method that provided the highest accuracy here, which is not a surprise because, well, this is the most advanced method we used. These are the confusion matrices we obtained for the classification of stellar light curves using random forest and XGBoost. If we look at these confusion matrix here of XGBoost, 96.3% of the stellar light curves without eclipses were correctly identified by the model. 96.77% of the light curves with exoplanets were correctly identified by the model. And 96% of the stellar light curves with eclipsing binaries were correctly identified by the model. So again, we can see that the accuracies are all very similar, very high for all classes of objects considered in the analysis. And the situation here with random forest is very similar. So in summary, we can say that in this case, random forest and XGBoost were the most adequate methods to classify stellar light curves in those 3 categories that I mentioned. And now my final conclusions. So all machine learning algorithms we tested here were adequate to classify the nuclear emission of galaxies using only photometric parameters. They provided accuracies of nearly 95%, almost all of them. Analysis performed using only broadband and only narrowband magnitudes also resulted in accuracies of nearly 95%. For the classification of stellar light curves, we concluded that the best option was to use the periodograms of the light curves as input parameters. And we also noted that the use of the Butterworth filtering to remove high-frequency noise from the curves resulted in improvements in the accuracies of the methods. In the end, random forest and XGBoost were the most adequate algorithms to classify stellar light curves with accuracies of higher than 90%. And that's it. That's all I had to say. Thank you.
Thank you very much, Roberto. Does anybody have any questions?
Alô? Pedro.
Tá desligado.
sometimes you have a mixture of, many times you have a mixture of AN, starburst ring, and since you are using SDSS with maybe a scene of 2 or second, you have a mixture. For those cases, they will appear in the mixing zone always in the BPT diagram, or are they mixed and they could explain the 2% of the ones you see?
Possibly. At the moment, let me put the correct slide here. At the moment, we are not including the transition objects. I think you're referring to that, the transition objects, in our data analysis, but that's our next step. We intend to include and try to perform the classification using 4 categories. The 4th category would be transition objects. And also, we believe that the use of higher spatial resolution data will also change these results a lot. But we intend to do what you're mentioning, yes.
Hi, I have a question about the redshift range of those galaxies. What is the range?
Between 0.001 to 0.1, or less than 0.1, not more than that. Not more than that.
And in the same way to Pedro question, do you plan to include also galaxies without emission line?
A high redshift?
Without emission lines. A passive galaxy.
But possibly, but for what purpose? Without emission lines to classify what? Exactly?
Because in images, we don't know what is a star-forming galaxy, a AGN, or a passive galaxy. So it will be interesting to have that classification also.
No, perhaps we could try to classify galaxies without emission lines using this, using only photometric parameters, just to see what happens. Because in this case, in certain cases, we have obscured AGNs or obscured H3 regions, and there are lines, but we cannot see them very well. So if we use photometric parameters, that could work. So yeah, I think we could try to apply this methodology to galaxies without line emission. That would be interesting.
Thanks.
With regard to the study that you did with light curves of stellar binary systems or exoplanets, what kind of sample did you use, for instance? For instance, in the case of eclipses, because you said that you got with those two methods, you could get a resolution of 90 or 96% of success in determining which sources in that sample reflected the passage or eclipse by an exoplanet, right? So what kind of samples and what is the resolution, the degree by which you had to constrain your sample in order to get this
I don't remember the actual parameters from the Kepler Public Data Archive, but yes, we selected all light curves with the same instrumental configuration, let's say. They were obtained exactly with the same configuration, but there's more than that. To perform the training of the algorithm, well, we required light curves with classifications from the literature. So we needed light curves with confirmed exoplanets and light curves with confirmed eclipsing binaries from the literature. But that's not all. We also needed good light curves, because many times when we searched for a light curve that, according to the literature, that light curve contains an exoplanet. Then we go to the data archive and we find a terrible light curve. We can see barely any eclipse, and there is a lot of instrumental artifacts, and we can't use that. And that's why this sample here is much smaller than in the case of the classification of the nuclear emission of galaxies, because it's very hard to find sufficiently good light curves to train the machine learning algorithms. But that's it. When we were searching for the light curves, we always selected the same instrumental configurations to perform the training.
Right.
I just don't remember the exact parameters, but yeah.
Right, but the sample was more or less, let's say, homogeneous in this sense. Okay.
Certainly.
Okay, thank you.
Thank you very much, Roberto. I have a question if nobody else has, or while people are thinking. The obvious thing that you would like to do is maybe to use now LSST data, new LSST data, to do some determination of these classifications, for example, for galaxies. But then there are two problems. First, you may not know the redshifts of everybody, because I understand you're using SPEC-Zs, spectroscopic redshifts. And the other thing is that the universe is more than just these three classes.
But
So
I'm using the photometric redshift.
using the photometric.
Yeah.
Oh, okay. Because I guess you never said that. I was thinking, wow.
I'm so sorry.
I see. So you are using the photometric redshift from S+.
Yeah.
I see. Okay. I see. Okay, and then what do you do about the classes that are not represented in your? So they are going to be badly classified, or what? Because I imagine that's what, right? You have a large number of galaxies, and you want to do this classification. How do you go about that?
Perhaps some objects do not fall in any of the categories. Perhaps that's what you mean.
Okay, and then those will be the
Uncertain classifications, but we can also try to, like he said, actually, try to include transition objects in as an additional category.
I'm more worried about passive, because there will be a lot of passive galaxies, right?
Yes, and of course, yes, an additional category could also be passive galaxies. Why not? Perhaps that would be the case.
Thank you. Anybody else? Amanda?
Just a technical question. The error in the magnitudes play a role in your classification?
They
somehow?
may play a role, but I'm not sure about what is the error in magnitudes in the case of S+, Claudia. I don't remember. Do you have any?
Because the magnitudes have errors, so that's what I'm. So how you would account that in your classification?
This data here used for the classification of the nuclear emission of galaxies came from the same source. The magnitudes came from the same source, S+ in this case. So the errors were essentially more or less the same, let's say. The problem would be if we try to mix in a single sample data from different sources. Then we could have a problem. Higher magnitudes with higher uncertainties could affect the training of the methods, and that could be a problem.
Yeah, that's what I was thinking, because some of the blue bands may have a little bit higher errors, so that could somehow be affecting the analysis. That's what I was thinking.
In this case, probably the bluer bands do have higher certainties. But since, again, all galaxies came from the same source, they are all affected by the same problem. Then in this case, it's fine. The problem would be to mix galaxies from different sources.
So, and the magnitudes are what type? It apertures, auto, do you remember? Just for curiosity.
Aperture magnitudes.
Okay, that must be 3, similar to Sloan, I would guess.
Yeah.
Okay, thank you.
Thank you. Anybody else would like to say anything or ask any further questions? Or Roberto, any final words?
No,
thank you so much, Roberto, for the very clear.
Thank you for the opportunity.
Okay, thank you for coming here. Thanks a lot.